the apparatus we're going to do. Now, I built the circuit. You're not going to have to build the circuit, but I want you to at least have some understanding why this is here. Okay. This is a very, very old feedback trainer. It used to be you did the electronics. Remember we talked about a PID control using op amps? Well, that's basically this section over here is a PID control with op amps. We're not going to muck with that because it's old-fashioned. You're never going to see it in industry. What I'm doing is I'm using the amplifier, the servo amplifier, and I'm taking an output from the I/O card, sending it through an op amp, and then sending it to the amplifier that runs the servo motor. The reason for this op amp is the I/O card that this thing has in it can generate minus 10 to 10 volts. This needs 15 to minus 15. So the op amp is basically doing a 1.5 times gain. So I can get full scale range to this device from this. So I'm going from minus 10, 10, minus 15, 15. Then on the other side, here we have velocity, which really is a tachometer. So this is generating a voltage based on the speed of the motor. Then I'm putting that through a voltage divider to do a basically a 1.5 times divide by 1.5. So it scales it to 10 and minus 10 for the I/O card so we don't fry. There's a cap on here just to filter a little bit, get rid of some of the noise. So what we're going to do, and this is step one, is you have to calibrate the speed for the tach. So what you need to do is spin the motor, measure it using a hand tach, which we have here, and then calibrate the output of the tach to RPM. So just like you did the thermistor, you're going to do various points, collect data, and do a straight line approximation for RPM versus the voltage. Does that make sense? Do you remember all that crap from the thermistor? We did it so long ago. So, but what we have to do is we have to send an output to this to drive the motor so we can take a measurement. So this is what I've got going on here. This is the power button for this device. Now, most of the time this is going to happen. First thing you have to do, make sure your output is at 0. So you're going to send to output, analog output 0, a 0 volts. That's what I have here. I'm just doing a direct control. If the motor is spinning, you need to adjust this until it stops. That's good. Temperature does affect that, so even if you zeroed it 5 minutes ago, it might actually change a little bit. So now I have 0 speed, 0 output, and now I'm going to slowly start to take measurements. So I'm going to put out 0.1 volts. So now the motor starts spinning, and then I'm going to take the hand tach and I'm going to shoot for the block. I want to be between 2 and 8 inches away, and right now I got a 490 about RPM. I take it a couple times just to make sure. If you get too close, it gives you an incorrect reading. If you're off the line, it goes nuts. So 492 about. And then you're going to increase this, 0.2, do it again, 0.3, so you get points on a line.
So you want us to do that in Excel, or is it something that's done in?
you're going to have to do a output channel in here and an input channel in here, so you can see, so you can adjust the output, read the input. Then you can do the calibration in Excel and do the same thing with the calculation block that we used for the thermistor. Use that to then come up with a speed. I don't know how close I was. Let's see, 960 is what my calculation came up with. And I'm at 971, and it's really jumpy because it's a little noisy, but that's expected. So that's step one. The other thing you can do with this, just so you're aware of it, is I'm also graphing it. But if I do a large step jump, oh, not 10, 1 volt will be just fine, thank you very much. I'm shutting this down just to show you. You remember we talked about a step response, an open loop test? I just did that. I changed my input or my output from a 0.2 to a 1. So that is my output change. And the speed change or the amplitude change of my output is shown here. Notice again, it doesn't change instantaneously. Physics says nothing changes instantaneously. So this is my response curve for that step. So you can get that information and do an open loop test, which might come in handy later when we do PID control. But the first thing is to calibrate the speed. If you notice here on the wheel, this took me all day to do. The tachometer is using light to measure. It needed a black and then a reflective surface. So that's what you're shooting for, is really, that's what takes the measurement of the speed. So the first thing you're going to have to do is come up with the VI for doing this test. And then we're going to add to it, we're going to use speed, then as a measured value, then we're going to build a PID control loop. If you notice here, don't fiddle with this while you're testing for this one, but this is a magnet. Does anybody know what happens when you put a magnet on a spinning metal disc?
Creates a magnetic field.
Creates a magnetic field, which does what?
Creates a current.
Creates a current.
Stores energy.
But what's the effect on the motor?
Slows it down.
It puts a load on there, because now it's having to go through magnetic lines of force, and it's actually acting as a magnetic brake. So this is going to be our process upset for your PID control loop. That we're going to put a load on there, and when we put the load on there, we should see the PID control loop speed up to try to keep the motor going at the same speed. So that's what that's for. We can also do position control. That's a little harder to do, and I'm not really ready for that one yet, so I think we're just going to concentrate on speed. It is a very simple control loop. As I said, I have another one of those. Unfortunately, this wheel moves in and out, so it makes all sorts of nice sounds when it starts scraping against metal, especially when we use the magnetic brake. So, analog in, analog out, going directly to points, is the first thing you have to do for this. And then doing graphs. You don't have to combine the graphs, it would be nice, but it's a real pain in the ass to do it in LabVIEW. Have them on top of each other, it's a pain. It can be calibrated. I did get actually a perfect straight line on my calibration. I got an R² of 1, which shocked the shit out of me. So, that's step one. Any questions? You can write the LabVIEW, then come over here, put it on this computer, test it, go back and fiddle with it if you have to.
What was the channel again?
Channel 0 for the output, channel 3, non-differential for the tachometer. And I'll write all that stuff up, but I don't have a write-up for this yet. One other thing I want to mention, and I probably should do this, but I will. When you did the data point, let's see here, let me call it a new VI here. File, new. When you did read. When you did this, create instance. You remember doing all that stuff and acquiring a signal. I'm going to do an analog voltage, analog